last week. This is still Provakar. Provakar was a student at University of Connecticut, was one of the first students working on the Super BigBite experimental program at Jefferson Lab. So did a lot of setup of the detector, a lot of the calibration, and is now presenting for the first time the physics results from the GMn experiment. So he'll give us an overview of all of that. And he joined us as a postdoc back in December.
Yep, thanks so much, John. And let me begin by thanking the organizers for this opportunity, and thank you all for being here. Today I'll talk about I'll share with you the preliminary results of SBS-GMn experiment, which ran in Jefferson Lab about 3 years ago for the high precision measurement of the neutron's magnetic form factor to unprecedented Q-square regime. So I'll begin with a brief introduction to the nucleon form factors and how they relate to the structure of the nucleons. And from there, I'll give a brief overview of the SBS program at Jefferson Lab with a particular emphasis on the SBS-GMn experiment. And then I'll talk about its physics analysis methodology, underlying challenges, and finally show the preliminary results. And then I'll conclude with a brief summary and outlook. So we are interested in elastic electron nucleon scattering. And here is the tree-level Feynman diagram for such a scattering process. And this is the associated scattering amplitude. So the leptonic vertex is very well understood in the framework of QED. And that's what makes electrons an excellent probe inside the nucleons. And the hadronic vertex encodes the electromagnetic structure of the nucleons in terms of this F1 and F2, which are known as the Dirac and Pauli form factors, respectively. And these are the functions of Q squared, which is the squared force momentum transfer in the scattering process. And its magnitude determines the resolution with which we can probe inside the nucleon. But it is more advantageous to define a different set of form factors in terms of F1 and F2, just some simple linear combinations of them. And these are Ge and Gm, which are known as the Sachs electric and magnetic form factors, respectively. And so in this formalism, the normalization is such that at Q squared equals 0, G and Gm represents the static properties of the nucleon, like their charge and magnetic moment. And in terms of G and Gm, the differential cross-section for the elastic electron nucleon scattering in the one photon exchange approximation takes this form. And this is also known as the Rosenbluth formula. So one advantage of G and Gm you can immediately see here is that in this expression for the differential cross-section, we don't have any cross-term involving the form factors. And another advantage is that in non-relativistic limit, G and Gm has well-defined meaning. So they relate to the 3D Fourier transform of the spatial charge and current distributions within the nucleons. But at higher Q squared, such density interpretation breaks down because we need, to draw some similar density interpretation, you need relativistic corrections, which are large and model dependent. However, there is a model independent way to draw, to connect the nucleon form factors, even in the relativistic limit, with the transverse charge distribution of the nucleons in the infinite momentum frame, where the observer is moving towards the nuclear at the speed of light and vice versa. So here on the left plot, I'm showing the transverse charge distribution of a longitudinally polarized proton, and on the right, I'm showing the same but for a neutron.
Yeah, I have to make a brief comment here about
Yes,
your previous slide. The non-relativistic limit for which the Fourier transform is valid is only when the quarks within the nucleon are moving non-relativistically. It has nothing to do with Q squared.
Right, okay. Yeah, thank you.
I also had a question more on the next slide.
Yes.
So the non-relativistic limit, that is basically a 3D picture. But the relativistic limit, you're going to 2D.
Right.
So what does it mean going from 3D to 2D, and how does that work? And put it another way, what do you do in the pretty relativistic limit in between those? Or
so this is so this picture is at the high x, right? So where most of the momentum is going to just one core, and then so for the case of neutron, it is dominated by d core, so you see a concentration of negative charge, but non-relativistic limit, I think you can it simplifies to just this kind of Fourier transform, but I don't know, probably does that at all answer your question? Or probably I didn't really understand. John, do you have any?
Well, I can say two things. So as Jerry says, it's not, the relativistic limit isn't a question of what Q squared, it's a question of the relativistic corrections to the structure. So there isn't a nice, not so relativistic limit or picture.
Right.
The other,
The problem is that to have a density, you have to have a matrix element of a density operator between states that are the same. Now, when you're working with relativistic composite systems, the actual internal wave function depends on the total wave function, the total momentum of the nucleon. So in the initial state, the nucleon has, say, 0 momentum, and in the final state, it has 3 momentum Q. Those internal wave functions are generally different. In other words, the wave functions are not boost invariant. But if you work relativistically in the front formalism, boosts in the transverse direction are kinematic, that is independent of interactions. So that's why transverse direction is 2 out of 3, and that's why you have to go to 2 dimensions. So the point is to have an actual density, you need to do it that way. I hope that's clear. But basically, the wave functions are generally, the internal wave functions are generally not boost invariant. They depend on the momentum of the nucleon. Non-relativistically, in Galilean invariance, you can write the wave function as a product of an overall plane wave factor times something that depends on the individual relativistics. You can't do that relativistically.
There is just not a clear-cut way to do it. Right? So there is not just a way to do it in relativistic sense, like scenario.
You don't
like
have a factorization
Right.
between the total momentum and the internal wave function, unless the total momentum is in the transverse direction.
Right.
and then the other thing is these 2D distributions, it's tempting to just think of them as just, okay, integrating over the longitudinal, or just, you boost and it flattens like a pancake usual picture, and it's just the remaining 2D structure. But so basically the center, 0, 0 is kind of the center of mass of the proton, and in the infinite momentum frame, if you have a high X quark, it pretty much defines this, carries all the mass, so it defines the center of mass. So you get features that would not come if you just integrated over a 2D, or if you integrated over Z in a 3D distribution. So the transverse distribution is.
Is this related to this issue that people bring up about inadequate localization because the Compton wavelength of the proton is large?
Yes, it's why the non-relativistic limit is right. It's why, that's why, it's a nice way of explaining why the non-relativistic limit doesn't work.
Okay.
Nice. Okay, thank you. Yeah, so just to finish, this parameter B is the distance from the center of momentum, and the brightest color here represents highest value and the darkest represents lowest. So as I already mentioned, that in this picture, we see a concentration of negative charge at the core of the neutron. So, not just these 2D charge distributions, like the measurement of form factors, the significance of it is far-reaching. Because they also, being among the most fundamental observables, they provide powerful checks to prominent QCD theories such as lattice QCD and help improve their calculations. And also, it is necessary to know the form factors precisely, to be able to extract GPDs, generalized pattern distribution moments from hard exclusive processes. And that in turn facilitates the three-dimensional imaging of the nucleons. So, and it is also possible to do flavor decomposition of the nucleon form factors if we assume charge symmetry in this following form. And that reveals very interesting results. So in 2011, Kate et al. Did such a flavor decomposition by using the existing form factor data, and they saw like a dramatically different Q-square dependence of the up and down quark contributions to the proton form factors. So the up quark form factors shown in black here scales as 1 over Q squared, whereas the down quark form factor shown in red here scaled as like 1 over Q power 4. And a possible explanation of this behavior invokes diquark degrees of freedom within the nucleon. So the argument goes like this. The scattering from this up quark is dominated by scattering from the lone outside quark inside the proton. So it just requires one gluon exchange. And then for the down quark scattering is essentially probing inside the die quark, which requires two gluon exchange. Otherwise the die quark will fall apart. So, so this interpretation, this kind of information is profound. But as you can see, they could only go up to like 3.5 Q² because it is limited by high Q² form factor measurements. So it is highly desirable to extend this kind of decomposition to higher and higher Q². And that will require extending the high precision measurement of all four form factors to higher momentum transfer. And that's where the SBS program comes in. So before getting into the SBS program, I'll give a very brief overview of the Jefferson Lab because I thought some of you may not be familiar with it. So Jefferson Lab, or JLab, is a DOE-owned national accelerator facility located in Newport News, Virginia. And the continuous electron beam accelerator facility at JLab can deliver up to 12 GeV continuous wave electron beam with unparalleled intensity and precision. And that's what makes JLab kind of the best place in the world for us, like for doing the kind of measurements we want to do. And JLab has 4 experimental halls, A, B, C, and D, where you can do fixed target experiments. And SBS program is running in Hall A. So the Super BigBite Spectrometer collaboration, or SBS, is running a series of experiments to extend the high precision measurement of GMN, GEN, and GP to unprecedented Q² regime. Sorry for the busy plot here, but I just want to bring your attention to these red data points here, which are SBS projections. And so you can see for GMN and GEN, the Q² increase is very large, it's about a factor of 2 to 3. For GEP, the Q² increase is somewhat smaller, but the precision will be much better. So for this talk, I'll be focusing on SBS-GMn experiment, which was the very first SBS experiment, took data from fall 2021 to February 2022 to extend the high precision measurement of GMN up to 13.5 J². But there are multiple challenges to do associated with such high Q² form factor measurements. For example, the elastic electron-nucleon scattering cross-section falls like 1/Q/12. And so to reach our statistics goals in a reasonable amount of time, we need very high luminosity, which results in very high rates. And so we need to make sure that we have high precision tracking in such a condition. And at the same time, we need to make sure that we can have simultaneous detection of high energy nucleons with very high and comparable efficiencies in such a condition. So to counter these challenges, primarily 3 detector subsystems were built. The first in the list is the SBS dipole magnet, which has a very large solid angle acceptance and also can reach very forward angles. And that was achieved with a cut in its yoke to make passage for the beam line. And also it had enough field strength to separate high energy nucleons by charge. And then second in the list is the hadron calorimeter, or HCal, which is a very large active area, and it's highly segmented too. And also it can detect both the nucleons with very high and comparable efficiencies and with very excellent position and temporal resolutions. And then last but not the least are multiple layers of gas electron multiplier, or GEM-based trackers, each with very large active area and has the capability of giving very high resolution tracking in high rate conditions. So with these 3 detector subsystems, 2 spectrometers were built. On the electron arm, we had the BigBite spectrometer, where we had the BigBite dipole magnet for momentum reconstruction, then 5 layers of GEMs for high precision tracking, then a gas ring imaging Cherenkov detector for ion rejection, a timing hodoscope for high precision time measurement, and which was sandwiched between a pre-shower and shower calorimeter for energy reconstruction and to provide the main trigger for the experiment. And on the beam right, or in the hadron arm, we had the Super BigBite Spectrometer, which consisted of the SBS dipole magnet for the separation of high energy nucleons by charge, and the hadron calorimeter for their simultaneous detection. So I think the collaboration got the name from this dipole magnet, like it's a Super BigBite Spectrometer magnet. So these detectors were installed in the fall of 2021, right before we started running for SBS-GMn. And that was COVID time, so it was a huge installation, and COVID added a lot more challenges to it.
What's the typical proton and neutron movement?
Oh yeah, it's from like in between 2 to 8 GeV.
Wow.
Yeah. So now moving on to the data analysis part of this talk. So this is this SBS-GMn experimental setup in GN4. So we took data on a 15 centimeter liquid deuterium target for production, and we simultaneously detected the scattered electron and the nucleons with our spectrometers, and such simultaneous detection enabled us to use the ratio method of measurement, which offers significant cancellation of a lot of systematic errors, like the errors systematic uncertainties associated to beam, target, trigger efficiencies, etc. And there are 3 major steps to get GMN in this method. First is to extract the quasi-elastic electron-neutron to electron-proton scattering cross-section ratio, RQE, directly from the experiment, and then applying radiative and nuclear corrections to obtain the elastic electron-neutron to electron-proton cross-section ratio, R, which is also known as the bond cross-section ratio. So here I should note that these nuclear corrections come due to the fact that we don't have 3 neutron targets. But the beauty of ratio method is that most of these corrections cancel out in the ratio. And so finally, we can substitute this R in the Rosenbluth formula and then get the proton reduced cross section from the global data parameterization, and then subtract a small term including GEN to get GM. So this is the high level workflow. And this is the kinematics of the SBS-GMn experiment. We took data at 5 different Q-squared points, 3, 4.5, 7.4, 9.9, and 30.5 GeV squared. So switching between, so as you can see, for each Q-squared point, we had different BigBite SBS angles and also the distance for each cal.
Sorry, you said the formula on the previous thing, you subtracted GEN.
Yes, GEN.
Is GEN known at these momentum transfers?
So
What to do for that? Yeah.
we also take it from parameterization, but it's supposed to be small, the contribution of it. So
Because it goes like epsilon over tau. So,
right.
okay.
Yeah. All right. So and then okay, yeah. So so switching between different Q-squared point meant moving around this multi-ton spectrometers in the hall manually, because we didn't have those on the rails. As I said, this was COVID time, so it required at least a day or two to set up for a Q-squared point, because it also involved survey alignment, and it caused significant challenges during runtime. But it worked out in the end. And as you must have noticed that for Q-squared equals 4.5 J-squared, we took data at 2 different epsilon points. So the high epsilon point was primarily dedicated to SBS-NTP experiment, which is a high-impact experiment that ran with parasitically with GMN for the first high-precision Rosenbluth separation of the neutron form factors to shed some light on the 2-photon exchange contribution in the elastic electron-neutron scattering. So it was a nice addition to the GMN. And here are the steps of high-level steps of data analysis. So we need to do from raw data event reconstruction, detector calibration, then physics observable extraction, and then we need to do some systematic uncertainty quantification, and only after that we can get preliminary results. And there are multiple iterations between detector calibration and event reconstruction that we needed. And each of these steps, as you can imagine, takes months to complete. And each can be a topic for a full seminar. But for this talk today, I will primarily focus on this physics analysis part and just show a couple of highlights for these two. So event reconstruction, what it means is it primarily means reconstructing the scattered electron track by combining bits and pieces of information from the different detector subsystems in the BigBite spectrometer. It also includes reconstructing the events from each cal and stuff. Since we are the first who use the SBS and BigBite spectrometer, at least the upgraded version of it, most of the event reconstruction code had to be written from scratch. So it had a lot of challenges and nuances involved in it. But I just wanted to mention one of the biggest challenges reconstruction-related challenges that we faced So here is a single event display that's showing all 5 gem layers that were in the BigBite spectrometer. And this is for Q square equals 4.5 J square, one of the low Q square that we took data on. And as you can see, due to very high luminosity, almost all the strips were firing, right? So, and that was making the number of 2D heat combinatories going astronomical. So that was not possible it was not possible in this situation to do tracking. So the remedy was to define a small track search region based on the best cluster in the BigBite calorimeter, and then propagating that constraint region backward to the front gem layers, and then doing track search only within that region. And that reduced the entire active area of the gems to just 2 to 3% of its entirety, making the reconstruction possible. But for this thing to work, we also had to make sure that we had very good gain matching and calibration of the BigBite calorimeter throughout the running, which was also not a very easy task to do. And then in terms of detector calibration, again, all the detectors were new, so all the calibration scripts had to be written from scratch and then validated, fine-tuned, etc. But we could, but after the second pass of calibration reconstruction, this is what we could achieve from our detectors. On the BigBite spectrometer side, we could achieve a momentum resolution of 1 to 1.5%, angular resolution of 1 to 2 millirad, vortex resolution of 2 to 6 millimeters. And for the hadron calorimeter in the Super BigBite spectrometer, we could achieve a time resolution of 1 to 3 nanosecond, and a position resolution of 5 to 6 centimeters. And all of these were in line with our expectations. So now moving on to how we do physics observable extraction. So let me begin by introducing you to the HCal delta X variable, which is what we use for yield extraction. So here the variable delta X is nothing but the difference between the measured proton or neutron position at HCal, right, that we directly get from HCal, and then the predicted neutron position at HCal, which we predict totally based on the electron kinematics. So when you plot this variable for hydrogen data, we get a sharp peak away from origin, and that is expected because the proton tracks do get bent by the SBS dipole magnet. But remember, our calculation of the predicted nucleon position always assumes that the nucleon, scattered nucleon is a neutron, so it should not get bent. So then when we plot this delta X variable for the deuterium data, we get 2 broader peaks, one at the origin, another coinciding with the hydrogen one. So the one at the origin must be due to quasi-elastic electron-neutron scattering, and the one coinciding with the hydrogen data must be due to quasi-elastic electron-proton scattering. So you can see we get a nice separation of proton and neutron events in this delta X variable, which we can then fit to get the corresponding counts to get our ratio of interest RQ. But so as you can imagine, you're doing a measurement at a very high Q square, so we have a huge contamination from elastics in our events. So we don't really get this distribution this nicely from the get-go. We need to apply a lot of analysis cuts to achieve it. And here is a list of cuts that we use. So first we have a set of cuts to select good electron tracks, which include,
Maybe you'll get to this, but don't you also have, don't want to use the word background, but multiple scatter interactions where you have interactions with both the proton and the neutron?
The final state interaction?
Well, no, and I'm using analogy from vector methods where, photon, if it interacts with a dipole, interacts with both of the nucleons. Maybe that's less of an issue for elastic scattering, but you could still have the electron, interacting with both nucleons exchanging a photon with each. It just seems a little simplistic to say you hit the proton or the neutron and not both.
Well, it's an electromagnetic interaction, so we only allow first order.
Yeah.
Well,
There's no
multiple scattering within the deuteron for the electron.
But you can have the photon fluctuate to a QQ bar dipole and then interact hadronically, and then
It's real for them.
okay.
Yes.
Think about it.
And in any case, you can have issues like that where you hit the proton and it scatters with the neutron on the way out, and vice versa. So
Okay.
may not get defined this way, but basically you have the electron and the nucleon energy. You're basically putting a cut to have an exclusive, so that you can't have another high momentum nucleon
This
somewhere.
is at x near 1, so
Okay.
the fluctuations are dead. Don't.
Okay.
So there are a lot of reasons, but the final state interaction, we'll get to this.
All right. Okay. Yeah. So here is a list of analysis cuts that we use. So first we choose. We have some cuts to select good electron tracks that include cuts like number of gem layers that had hits, then cut on vertex C, E over P, and BigBite optics validity. Then some PID cuts for prime rejections that includes like pre-shower energy, range, cluster size, etc. We also have cuts to select good HCal events, which includes cuts like HCal cluster energy, HCal active area. And since we're doing coincidence measurement, we definitely put a cut on the coincidence time between the shower and HCal. And we also, to do our quasi-elastic event selection, we put cuts on variables like W squared, which is the squared invariant mass of the virtual photon nucleon system, and delta Y, which is the difference, which is the difference between the predicted and observed nucleon position, but in the non-dispersive direction, like same as delta X, but in the non-dispersive direction. And another very important cut for our analysis is the fiducial cut to match the acceptance for proton and neutron events, which are not really the same to begin with. So just let me give you an example. So this is for q squared equals 3j squared, the lowest q squared to data on. And here on these plots, I'm showing the envelope of the expected neutron and proton positions. And this green rectangle here shows the physical boundary of the HCal. So the proton envelope is shifted because of the SBS dipole magnet. But you can see the acceptances of the neutron and proton are not really matched without any cut. But then when we apply the fiducial cut, which is shown in this blue rectangle here, they effectively matches the acceptances of neutron and proton events, which are essential to reduce a lot of systematic errors in the ratio. So this is very important for us to use. And this plot very nicely shows the effects of our analysis cuts on the delta X distribution. So here, this distribution with the lightest shade of gray, it shows all events without any cuts, and you can barely see the proton and neutron peaks. Then when you like add on cuts like good electron, good HCal, and finally W squared and delta Y, it nicely resolves the proton and neutron peaks, which enables us to do the extraction of the ratio. So the correlation between this W squared and delta X variable very nicely show the process of our quasi-elastic event selection. So here, this again for q squared equals 3j squared, the lowest q squared took data on, and here you can see the quasi-elastic spots near the mass of the nucleon as expected, and then the inelastic significant contamination from the inelastic event shifted towards the high W squared region. So with the well-formed W squared cut, as shown by these red line here, we can effectively select our quasi-elastic events and reject the background. And this is nicely shown from this delta X distribution, which had this cut implemented. And there you can see very little background is remaining, and the background is smooth and can be, like whatever is remaining can be modeled very easily. So here's examples from same set of plots, but for different q squares. So while going from left to right, I'm going from lowest to the highest q squared. And here, if you just focus on the top row here, you see like when you increase the q squared, the quasi-elastic peak in the W squared distribution get broader, and also the contamination from elastic increases significantly, which is expected. But in each cases with a well-defined W squared cut, we can very effectively select our quasi-elastic events of interest and reject inelastic background. And also with the increasing q squared, the position resolution increases, which giving a very fine separation of the proton and neutron events even at the highest q squared point, which is the most challenging one, as you can see here, right? So which is very reassuring. But as I've mentioned before, it is necessary for us to fit this distribution to be able to extract the corresponding counts and the ratio. So our philosophy for fitting this distribution is to, generating realistic signal shapes from Monte Carlo, and then combining those signal shapes with some background model, and then do the overall fit. But as you can imagine,
Sorry, just since you mentioned that, the resolution in delta X is improving. Is that an improved resolution of the nucleon position at higher momentum, or is it something to do with the Jacobian between the electron kinematics and the proton?
Yeah, so it is mainly kinematic focusing, to be honest, because you have and also at the same time, so when you increase q square, the nucleon momentum also increases, so that gives you bigger and bigger cluster in H tau. And since this energy and you have it's weighted centroid, so it gets better and better resolution.
So combination of both.
Combination of both. So as you can imagine, generating realistic signal from Monte Carlo is challenging, right? But we have put in a lot of effort to have this machinery, and which consists of multiple large-scale software libraries. So this is the high-level workflow. So first we generate quasi-elastic events with realistic physics effects, and then we run those events through GN4-based detector simulation, which has our experimental setup implemented with all the details that we want, and then we digitize those simulated events to generate pseudo-raw data. And after that, we use the same event reconstruction machinery that we used to reconstruct the experimental raw data. Using the same machinery, we reconstruct the pseudo-raw data and then apply the same analysis scarce, right? And that only then we can generate physics histograms from Monte Carlo and data that can be compared on an equal footing, right? So, but it is necessary for us to validate our machinery, our simulation machinery, to see if it really has all the effects that are known to be present in data. And the best variable to look at is the W-squared distribution, because that is very well known for quasi-elastics. And here what I'm doing is I'm just plotting the W-squared distribution using pure quasi-elastic simulation for all the Q-squared points. So when you go with the fading shade of gray, we are going from the lowest to the highest W-squared, and you can see here the kinematic broadening of the W-squared distribution is very nicely captured in our simulation, right? And then next, we'd like to do a direct comparison of the W-squared distribution between data and Monte Carlo. So here black is data, and then green is the quasi-elastic signal, pure quasi-elastic signal from simulation. And this magenta, is background, inelastic background, again from simulation. And as you can see in this, and this red is the overall fit that we obtained by combining these two. There are only two fit parameters, just individual normalization for this the signal and background. And you can see, in the entire region, the agreement of fit looks really good. And this kind of plot gives us enough confidence about our simulation machinery, and with that we can move on to do this data Monte Carlo comparison for the delta X distribution, which is what we want for our yield extraction. And here is an example of such fit for q squared equals 7.4 J squared. So this is the middle q squared point we took data on. Here again, this black is data. This red is the overall fit, which was obtained by combining this proton and neutron signals from quasi-elastic simulation and this magenta, this background from inelastic simulation. And so we have only three fit parameters: one overall proton normalization, and then RNPSF is relative neutron to proton normalization, and B is overall background normalization. And just by looking at the residual, you can see the overall, the agreement of fit looks really good in the entire range of interest, right? So, but the question is, how do we get GMn from a fit like this? So, well, we begin with an assumption that our quasi-elastic simulation accurately represents all the physics and detector effects that are known to be present in data. And as I've mentioned, we put in a lot of effort to make sure that that is the case. So with that assumption, this fit parameter RNPSF, which is the relative neutron to proton normalization, becomes just a measure of the discrepancy in the neutron to proton bond cross-section ratio between data and simulation. So all we have to do is multiply this fit parameter with the bond cross-section ratio that we get from simulation to get the bond cross-section ratio from data, right? So then the only step remaining is to substitute this R in this Rosenbluth formula that I have shown before to get GMn, right? But as you can imagine that, so we have to have an optimized set of cuts. Is there any question there?
Well, actually, yeah. So this question came up of other processes, and
Right,
so, for example,
yeah.
finite state interactions. And so I assume you don't have that modeled in your event
No.
generator.
No, we estimate final state interaction afterwards.
Okay.
Yeah.
Because I mean, for the most part, if you transfer any significant momentum from the struck nucleon to the one that it hits, then it doesn't pass the W squared cuts and all the rest.
Right.
You can have grazing interactions, which probably don't matter much and should cancel pretty well between the proton and the neutron.
Right.
But if you have like an exact head-on, so that your photon hit a proton and it knocks out a neutron, if you get very unlucky and it comes out sort of with the full momentum, that's something where you get a little leakage between protons and neutrons and vice versa. The probability of that happening should cancel, but since the proton cross-section is larger than the neutron, it will adjust it.
Yeah.
And so that's what, so you look at that charge exchange piece as the final
Yes.
interaction? Okay.
Yes.
I just
So
haven't
it's
seen
like-
that part before.
So yeah, thank you. Great question. So yeah, what I was mentioning is that so our RNPSF extraction is sensitive to the cuts we choose because we need to make sure that we need to optimize our cuts so that we can make sure that we have the best possible signal to background, and also our cut does not affect the neutron and proton events differently, because if that happens, then we have a biased RNPSF extraction. So we need to avoid that, and the approach we take to avoid that is that so we study the stability of the experimental observables like RQE, the quasi-elastic electron-neutron to electron-proton scattering cross-section ratio, or just RNPSF I just showed in the previous slide, as a function of the cut variables in the region of our interest, and then we choose the cut range that excludes the region of instability. So just to give you an example, so here I'm plotting, on the left I'm plotting RQE as a function of the vertex C variable, and on the right I'm plotting RQ as a function of E over P, like two of the cuts that we use. And in these vertical red lines is shows the region of the cut region that we selected. And as you can see, it chooses the region in which the ratio was stable. But we have done it for all the cuts, right? And this is a summary. So this is not to, sorry for the busy table here, not to overwhelm you with information, but just I wanted to show that we have done this rigorous cut optimization study for all the different cuts that we use and for all different Q squares, right? And then only after that we do our final extraction of RNPSF. So now, before getting preliminary results, the only step is to talk a little about the systematic uncertainties. So our measurement is systematics dominated. So we have multiple sources of systematics, including inelastic contamination, cut stability, nucleon detection efficiency, radiative correction, and final state interaction, like as we were discussing. It takes a lot of effort to quantify the individual systematic uncertainties for all this. So for the interest of time, for today, I'll only mention like how we do it for these two, because it was easy enough to do and it'll give you a sense of the process. But I'll be happy to answer any questions on any of these. So just to talk about the quantification for the elastics, the estimation of the inelastic contamination. So this is the data Monte Carlo fit that I showed you a few slides ago. So all we do is we do this fit using the quasi-elastic proton-neutron signals, but with different background models, right? So we can get our background shape from data by using semantic cuts. Then we can also get the background shape from inelastic Monte Carlo, as I showed before. We could also use some parameterization and stuff. What we do is for each type of, and we have like 6-7 different models to do it. And then for each cases, we do the fit and extract the corresponding RNPSF value, the fit parameter, and then we take a standard deviation of all these values, and then we quote that as the associated systematic uncertainty. So this is just a measure of our ignorance about the true shape of the background for these distributions.
Sorry, how did you get the shape for the data?
Oh, so so there are different ways to do that, but for this, what I did is, like I talked about the delta Y cut, right? So I just took an anti-cut on it, like just avoiding the region of interest.
So those three plots look so similar to each other.
Right. Yeah, they're not really that much different.
Even the ratios, it's almost exactly the same.
Yeah, that tells you like how stable our extraction is. So the due to the inelastic contamination, so if it was like changing really big, well, so for the highest Q squared, the change will be a little bigger. So giving you more like a higher systematic uncertainty due to this. But even at this Q squared, it was very small.
But the differences between them are small, but they're also comparables to the statistics. So it's small but not negligible.
Not negligible. Oh, definitely.
Well,
That's the
it's
we were
not
doing
compared
this.
to that.
Yeah.
So what is included in the inelastic?
What is included? Like the pine production, single pine, multi-pine, primarily pine productions and stuff. Basically, inelastic scattering that we cannot avoid. Like that has the bleed through from our our W square distribution. And then next, I wanted to talk a little about the cut stability, why we need it. So this is because I showed you that we do rigorous cut optimization study, but nothing tells us that this is exactly where you need to put the cut. So nothing tells us that. So that's why, but our result can change a little bit with different cuts. So to quantify that uncertainty, what we do is we vary of our cut variables, each of them by plus or minus 10%, by keeping the other cuts constant at their optimal values. And then for each variation of these cuts, we extract the RMPSF value, and then we take one standard deviation of the resulting RMPSF distribution and quote it as the associated systematic uncertainty. So that, so this is the table of our total systematic error budget. And so again, this is a busy table, but I just wanted to point out that the inelastic contamination, nucleon detection efficiency, radiative correction are the most prevalent sources of systematic uncertainty for our measurement. And I also wanted to point out that when you want to get GMn from R, the bond cross-section ratio, there are two additional sources of systematics. One is due to the protons reduced cross-section and GEN. So now with this in hand, we can go to our preliminary results. And these are shown in the red data points here. And and this black are the existing world data. So as you can see, for the low Q squared results, our low Q squared results agrees well with the existing world data, but the high Q squared results will significantly increase the region in which GMn is known precisely, right? And the precision of the highest Q squared point is expected to stay unmatched for many years to come, because I'm not aware of any other experiment that has been approved or taken data that will go up to that high Q squared. So this black line and the associated band, which is a little hard to see here, is from the global fit from 2018. And you can imagine when you reanalyze the global data with our results, how significantly it is going to constrain this high Q squared region. See? Yeah. Yeah, it is a little hard to see. Sorry for that. But it is like this, the band. Significantly enhancing our understanding for the neutron form factors. So one thing, so initially I showed the flavor decomposition of the nucleon form factors, and you can imagine that our results is going to have a big impact on those, and that is true. And I can show you. Oh, so I forgot to mention that here the uncertainties are the systematic and statistical uncertainty added in quadrature. But just to show you some impact on the quark form factors of our result. So here we did a flavor decomposition of the magnetic form factors of the quarks to get GMU, the magnetic form factor, the up quark in the black here, and magnetic form factor, the down quark in the red here. And you can see, and this band here is by doing decomposition from the global fit of all four form factors. And these data points are by replacing the GMN values from the global fit with our results. And the same here as well. And you can see it high Q squared. Our data dominates the uncertainty, right? And once we have the final results of GMN and reanalyze the global data, it is going to significantly constrain this extraction in the high Q strategy, which is very interesting. And it is also interesting to see how the Dirac form factor of the quarks look like with our results. So we do a flavor decomposition in the same way, and here I'm plotting the Dirac form factor of the quark multiplied by Q power 4 as a function of Q squared. And here black shows the up quark, red shows the down quark, and again the band is by doing the flavor decomposition from the existing global feed from 2018. And the data points are by replacing the GMN values from the feed with our results. As you can see, so at least for F1D, our results shows a noticeably different trend than it's expected from the global feed. And it shows a possible zero crossing of it around 10 J squared, which is very interesting because some theory expects it to not see a zero crossing around this, or some theories expect to see one. But our results definitely contribute to that debate and help and improve our fundamental understanding. But the error bars here, unfortunately, are not good enough for us to say anything definitively. But this is primarily dominated by GEN in this region, because there is no measurement of GEN in this region, as JD pointed out before. But the good news is the second SBS experiment, SBS-GMn, has taken data until 10 J squared, and once that is published, it will improve this situation significantly. And we expect a factor of 2 improvement in this current situation. And yeah, so that would be a huge thing. But with our results also, we see something that can be potentially interesting. So that brings me to my summary slide. So the high precision measurements of the nucleon form factors in a wide range of Q squared reveals their electromagnetic structure. And the SBS program at JLab's Hall A will extend these measurements up to and beyond 10 J squared, which will significantly improve the current situation. And then the SBS-GMn, which is the very first SBS experiment, finished data collection in February 2022 to extend the range of high precision GMN measurement up to 13.5 J squared. And the extracted preliminary results are in line with our precision goal and will vastly advance the current understanding of the neutron's internal structure. And also the implication of our results on the flavor decomposition is also very interesting and has potential of improving our fundamental understanding. And right now there are significant efforts going on to finalize our systematic uncertainties to be able to publish these beautiful results as soon as possible. So please stay tuned. And yeah, with that, I conclude my talk. Thank you very much. And this is the collaboration with not all the people. Are there any questions and comments?
I'll start with a quick comment. As a collaborator, thank you for not using R functions to quantify your uncertainties. If you don't know what I'm talking about, good. Just any better questions or comments?
Maybe ask in one of your last slides showing the crossing at 0.
Right.
I remember that your GMN is extracted assuming GEN is 0. And there was a GEN term in your extraction.
Yes.
So do you think there's some kind of correlation between that?
Between this zero crossing?
Because right now you're using, to make this plot, you can know both GEN and GEN.
Right.
GMN.
So I can just show you the individual contributions. So here. So probably hard to see. But so this is what goes into the F1D calculation. And you can see how much each part contributes to it. And the biggest contribution comes from GMN. Yeah. And then GN is very small. But the uncertainty of it is huge.
Yes.
So that's what.
So you mentioned you compare with some global analysis. Are there like other calculations you can compare with?
For the F1D? Yeah, so there are, let me show you. So, so these are from 2013 Deal and Crow GPD based calculation, right? And it showed, like, as you can see, no zero crossing in F1D, at least up to 6 chips, but I don't have, like, beyond this. But, we got some calculation. So there is a paper, I think in very recent one by Craig Roberts and people, based on Dyson-Swinger equation calculation. And they predict the zero crossing of F1D around like 6 chips squared or something like that. So there's still, a lack of understanding, I guess, or we need to better understand which one. Yeah.
So how much did GMN change compared to the global fit? Just 2 curves.
Right. It's a little hard to see from here, but so
the global fit
is this black line?
The black line.
Right. Is this black line?
Points.
Yeah, it shows a slightly slower fall off of GMN, but it's kind of within the error band. But the error band is really huge in this range with high chips because we essentially don't have any good data. It's just from the Slack data. Huge error bar.
I like huge error bars.
So what is that 2008 curve?
2008. Yeah. So this is this is based on covariant spectator model.
So this is a calculation.
Yes, it's theory calculation. And this Lohmann is vector meson dominance, and this Deal is GPD based.
But like the last two definitely, and maybe the first one, do involve fitting to the data, right? With the functional form that comes from the theory.
Right.
Many parameters.
And like with the GPDs, you tend to put in form factors and get out other things. So when you compare the form factors, sometimes it's a pure parameterization, and sometimes there's physics in it, and you have to look at the details. On the other hand, the band here, the only reason it doesn't explode more rapidly than that is because there is some physics constraint built into it that lets the uncertainty get big, but also doesn't just, it's not like a polynomial thread where it would blow up completely.
It might be interesting to look at the transverse charge densities.
Right.
We'll be talking to you about that later this week if you want.
I'll be around. I guess the small b values will change.
Right. Yeah, it would be. Yeah, we wanted to talk.
Well, and the flavor decomposition.
Flavor decomposition will be interesting because, well, I don't know if the zero has any particular meaning because you're integrating with an oscillating function to get the form factor. And, sometimes the zero has to do with a sharp edge in the distribution.
Right.
I don't know if that would happen here, but I don't think I ever looked at F1 D and U separately, at least not for a long time. But pretty impressive work.
Thank you.
Very challenging to measure these small cross sections.
Yeah, the detector's calibration was
Monstrous.
yeah.
Not as big as Elisa Rick, but a factor of 20 less people to do it, so it kind of balances out.
Right. Yeah.
For me, the impressive thing was the picture of the collaboration where you could actually recognize individuals.
Yeah. That makes sense. You are familiar with a much larger collaboration that you had. Yeah, it's small, and also not all the people are always active. But a few people are missing. I think it balances out.
Where's John in the picture?
Huh?
Where's John in the picture?
Oh, John. Yeah, John is missing.
I was in California at that time.
Yeah.
That's probably about a fifth of the total nominal collaboration?
Yeah, but no.
Wow, that's misleading.
Yeah, well, let's see how you do in your most recent Elise picture.
How do these results change interpretation, quarks and diquarks?
Oh yeah, so I just got some because Bogdan talked to Craig Roberts, and he like according to him, this zero cross. If we see a zero crossing, that would mean that we have a correlation in the proton wave function. If we are just talking in terms of hadronic scale.
Proton wave.
Yes, so like a isoscalar correlation or also like an isobector correlation. That's what his take was on.
All right, any other questions? Let's thank Provakar again.
Thank you so much.